In this video, I'm going to be showing you guys how to solve integrals using partial fraction decomposition. Now, some integrals are basically impossible to solve, but again, as always, algebraic techniques, right? Partial fraction decomposition is an algebraic technique, and it basically just allows you to manipulate your integral to make it so that you can use your very well-known rules like reverse power rule or the natural logarithm identity. Now, what do you do first for partial fraction decomposition? Well, the first thing that you do is recognize the factors inside the denominator. So what are the factors? Well, the factors are x minus 1 and x plus 2. Now, technically, 1 is a factor, right? But we're not going to care about that. Anytime you see a factor 1, ignore it. All right. How about a... Wait, not how about. The next step, you write down a. It could be any letter, to be honest with you, but usually people use A, B, and C, and D in order. But you write down A and then one of the factors, right? Plus B over the other factor in your denominator. Okay, now that you have this format, really the next steps are logical. So, in order to get this function to turn into the integrand, the original function, you need the same denominator, correct? Well, in order to have the same denominator, you need to multiply the a fraction by x plus 2 over x plus 2, right? X plus 2 times x minus 1 is equal to the original denominator. And in order to multiply this b fraction into the original denominator, you need to multiply b by x minus 1 and the denominator by x minus 1 as well. So now that we have this, what we can actually do is distribute a into all of these parentheses into x plus 2. So we get ax plus 2a over x plus 2, x minus 1, plus b times x minus b over x plus 2, x minus 1. Well, we can actually combine these two fractions now that they have the same denominators. So we can get a times x plus 2a plus b times x minus b over x plus 2, x minus 1. Well, since the denominators in both our integrand, or original function, and this newly ab function that we wrote down are the same, we can just completely ignore the denominator. All we care about is the numerator in this case, right? So how do we solve for the a and b values? Well, ax plus bx here is equal to some value times c, correct? Some real number times c. But look what we have here. We don't have any values multiplied by c. Sorry, multiplied by x here in the numerator. There's nothing. There's nothing that's multiplied by x. So that means that ax plus bx must equal 0. And we can kind of just get rid of the x value so that we get a plus b is equal to 0. Well, how about for 5? Well, 2a minus b is equal to 5, right? Since a and b are real numbers, you can add them together to get another real number. There's no multiplied by x, no multiplied by x squares in this terms. It's just 5. Now, we have here a very familiar, oh so familiar, system of equations. So in the end, you should get a system of equations for your partial fraction decomposition. And it's really just, it's really just, you can use any technique for this. You can use what's it called, elimination and substitution for this. So we'll just say that in this case, a is equal to negative b. So we can substitute. Actually, we can write down b is equal to negative a. That might be easier. B is equal to negative a, right? And we can substitute b as negative a into this next function. So 2a minus negative a is equal to 5. So that means 3a is equal to 5. So a is equal to 5 over 3. Well, if a plus b is equal to 0, that means b is equal to negative 5 over 3. All right, we have a and b values. That is the end goal for partial fraction decomposition. So in our original format here, this is what we wanted to use: a over x plus 1 plus b over x plus 2, and we solve for the a and b values. So if we rewrite this, we should get 5 over 3 times 1x times 1 over x minus 1 minus 5 over 3 times 1 over x plus 2. Correct? I just substituted in the values for a and b here. And what we can actually do is rewrite the integral like so. Since this actually is equal to this. These two are the same things, the integrand and this newly algebraically manipulated function. So if we rewrite everything, we get 5 over 3 times 1 over x. You know, wait, why am I doing this? I can just move this. I can just move this on to the integral dx. All right, well, we can factor out 5 over 3 here. So 5 over 3 is factored out of the integral to get 1 over x minus 1 minus 1 over x plus 2 dx. All right, now we just need to use natural logarithm identities. So we have 5 over 3 times the natural logarithm of x minus 1 minus the natural logarithm of x plus 2. And there it is. Now, you can take partial fraction decomposition in a logical sense, but you can also just memorize the steps, right? The more you practice it, you can just, the steps become basically muscle memory in that case, in most people's cases. All right, let's go ahead and start by recognizing the factors of this problem. Well, it's not as obvious as the previous problem, but the factors are x minus 1, x minus 1 squared, and x minus 1 to the power of 3. These are the three factors of the problem. Technically, 1 is a factor, but we don't count that using partial fraction decomposition. Now we have our three factors. We can set up this problem. A over x minus 1 plus b over x minus 1 squared plus c over x minus 1 to the power of 3. All right, now we need to multiply each of these functions so that the denominator is equal to the original function. Well, in order to multiply x minus 1 in order to get x minus 1 cubed, you need to multiply a by x minus 1 squared. All right, x minus 1 squared over x minus 1 squared times, oh, that was not an a, times a over x minus 1. Well, now that you have this, let's go ahead and expand x minus 1 squared to get x squared minus 2x plus 1. So we're technically multiplying a by x squared minus 2x plus 1. If we do that, we get a x squared minus 2 times ax plus a over x minus 1 cubed. All right, we solve for the a value. What about for the b fraction? Well, in order to multiply this denominator into the original function, into the original denominator, you need to multiply the denominator by just simply x minus 1, right? So x minus 1 over x minus 1 times b over x minus 1 squared. Well, this just equals bx minus b over x minus 1 to the power of 3. Let's fix that b. b over x minus 1 to the power of 3. There you go. All right, what about for c? Well, for c, it's very easy. In order to multiply the denominator into the original denominator, they're the same. So you just multiply this by 1, technically, so you just get the same thing. X minus 1 cubed. All right, now that we have this, we can combine everything in the numerators to get ax squared minus 2ax plus a plus bx minus b plus c. Okay, and since the denominators are equal to each other, we don't have to care about them. So let's only worry about the numerator. This right here has to equal 3x plus 4. Right? The numerator of some fraction has to equal the numerator of the new algebraically manipulated fraction. So let's get this straight first. The only term that has x squared in it is a. But since the original function doesn't have any x squared values, a x squared is equal to 0, which means a is just simply equal to 0. All right, what about the 3x terms? We have 2a times x plus b times x is equal to 3x. Correct? We can actually cancel out all the x terms so that we get negative 2a plus b is equal to 3. Let's go ahead and erase this guy. And we can also write down the terms for 4. So the only numbers that can equal 4 are a plus c minus b, since none of those numbers have any variable values multiplied into them. It's equal to 4. All right, let's go ahead and solve for this one first. Well, since a is equal to 0, that just simply means b is equal to 3. This right here and this right here are important. Let's keep them. And if b is equal to 3 and a is equal to 0, then we can c is just equal to 7 in this function. So now that we have all the variable values, let's erase all the previous work so we can save room. And let's go ahead and rewrite our fractions. I can't outline everything. So if we rewrite our fractions, a is just simply 0, so well, this fraction just cancels out, right? B is equal to 3, so we get 3 over x minus 1 squared, plus c is 7 over x minus 1 to the power of 3. And this right here is our new integral. Actually, I don't have to erase that. Let's go ahead and move this up. Ooh, I'm running out of space. Yep, I'm erasing this. So this right here is our new integrand. And it's just simply a reverse power rule problem. So the integral of 3 over x minus 1 squared is just equal to negative 3 over x minus 1 to the power of 1, which is just itself. So negative 3 over x minus 1, and the integral of 7 over x minus 1 to the power of 3 is just negative 7 over 2x plus 1 squared, plus c, of course. So for this integral, we have x squared plus 2 over x times x squared plus 1. So let's go ahead and notice the factors. The factors are x and x squared plus 1 in the denominator. So we write down the fraction a over one of the factors x plus b over the next factor. Now here's the thing about this. If you have an x squared here, not, let's be very clear with this, not x plus 1 squared, just x squared, then you have to write down your format for the numerator in a different way. You must use bx plus 1, bx plus c, sorry, a power down. So the numerator has to be a power down from the denominator in a very general form. And also, if your, what am I writing? If your denominator was x to the power of 3, then you would have to use bx squared plus cx plus d. This is what I mean by general way. You're going to have a quadratic here with every single term of x, stepping down a power. But in this case, we just have x to the power of 2, so it's bx plus c. All right, now that we have bx plus c as our numerator in this case, let's go ahead and start doing the fraction decomposition once we've set it up. So in order to get the denominators the same as the original function, you have to multiply the denominators, the factors, but with each other. So we multiply the a fraction by x squared plus 1 over x squared plus 1. We multiply b fraction by x over x. All right, now that we have that, we have a squared, ax squared plus a over x squared plus 1 times x. And we have bx squared plus cx over x squared plus 1 times x. as well. So if we combine these two functions, we get x squared plus b plus a plus bx squared plus cx over x squared plus 1 times x. And keep in mind, the denominators are equal to each other, so we can just kind of ignore it. Now let's go set up our systems of equations. So we have ax squared plus bx squared is equal to what? Well, the only x squared term inside of the numerator is x squared itself, so we have x squared here. And we can actually cancel out all the x squares to get a plus b is equal to 1. Alright, now that we have this, let's go ahead and use cx. So cx is equal to, well, since there's no terms inside of your function that have the single exponent, x to the power of 1, right? Cx is just equal to 0. Therefore, c is equal to 0 in this case. So c is equal to 0. All right, well, how about for whole numbers? Well, a is the only only variable out of a, b, and c that don't have any terms multiplied by x. So a is equal to the simple only whole number inside the numerator, 2. All right, now that we have a is equal to 2, c is equal to 0, we can solve for b pretty easily, right? If a is equal to 2, b is equal to -1. Now that we have all the letter variables, we can just erase everything else. And we can substitute everything in to our setup function. So setting up is really the hardest part. This right here is really the hardest part. So a is equal to 2, so a over 2 is right here. B is equal to -1, so we actually have minus x over c is equal to 0, so we just put plus 0. Kind of omit that. So x over x squared plus 1. And this right here is our new integral format. Nope, now that we have this, we can just solve for it individually. Well, 2 over x, simple, identity, the natural logarithm. Identity, correct? And also, x over x squared plus 1, simple u sub problem, -1/2 natural logarithm of x squared plus 1. I'm not going to deal with all the u sub